And we're going to talk about capacitors and capacitance in an AC circuit and the project in the lab that you're going to do with that. So if you were looking at the lab job number 6, first page, it says one of the objectives is to test for an open, shorted, or leaky capacitor using an analog VOMM. It says VOM, but it means VOMM. What does VOMM stand for? Volt ohm milliamp meter. Milliamp meter. It doesn't read amps. It reads thousandths of an amp, right? It doesn't take big currents very well. To flow big currents through a, say, a Simpson 260, which is a very good analog VOMM, you've got to do certain things like move the probes so that it does a shunt and things like that. So for this project, you actually need to use a VOMM. Now, if you have one or you can borrow one, that's fine. We have one that belongs to the college. We have one that belongs to me I'm a little sensitive about, a Simpson 260 that is. And if, like I said, if you have a Simpson 260 or a similar analog, highly accurate VOMM, you might want to use it on the capacitor project because you need to see what's happening. You need to see. There are very few times when this occurs, but there are times when you want an analog meter so that you can see what's happening. We're going to do a thing called a kick test when we're looking at transformers, and you have to use an analog VOMM to be able to see the kick. Because if you don't have a needle, you don't have a kick. Okay? So there are times when you need an analog meter, and this is one of them. Now, I want you to look at the videos that I've already built, Introduction to Capacitors, previous chapters, and talk about RL circuits and capacitance. I'm going to solve an RL problem for you. We've already done that in the other class, an RL worksheet. Now, this is not just the capacitor project, it's not just an RL, it's RLC. Okay, there's a make video on capacitors so that you understand what capacitors do. Now, the first thing that this lab project says is you're going to check for if the capacitor is good, right? Because trying to do a project with a bad capacitor is not going to work out very well. So you probably want to know how to find a video on how to check a capacitor. So right there on the web page, it's not my video. And there we have the young man talking about it. That's fine. We're not going to watch this whole thing in class. I hope I'm not going to drop the whole thing out by doing this. Find out. Yes, I would. Okay, so how do I get rid of the YouTube portion? Go back. I can do that, I think. No, I think this has gone over to, I may drop the whole thing, but I'm going to have to take that chance. Okay. What's that? Get off me. Oh, shoot. Okay, no, I don't want that. I want to go back to my Moodle web page. How do I get to history? Okay. I should hit pause while we're screwing around with this. Now, the second item on your list, after you check the capacitor, make sure the one you're going to use is going to work, is you're going to make sure what the actual capacitance of the capacitor is. And it says use a capacitor checker. The required meter for this class and the 4th semester class is a Fluke 117, and it can check capacitors. It has that capability, so make sure that if you don't know how to do it, look it up in the instructions of your meter. Okay? Solve problems with a capacitor connected in series and parallel. That is basically the project you're going to do. Okay? Become familiar with RC time constant. That's the main thing you're going to do. The thing you're going to do to prove that you understand what the RL time constant or the RC time constant is you're going to create a circuit and you're going to charge it, and then you're going to discharge it, and you're going to watch how long it takes to discharge. And you're going to have to predict how long it takes to do that. So main part of this project is building this thing and getting it to time down properly. Now there's a couple projects where you're going to just put them in parallel, put them in series, see what they do. And I want to tell you or remind you, as the case may be, that capacitors you treat the exact opposite way you do resistors. You know that if series resistors, or if resistors are in series, you just add them up, right? Well, you treat them exactly the opposite way you would do resistors, so you treat it as though it were a parallel resistor. So if you've got series capacitors, you treat them like they're parallel resistors. So you do it by the reciprocal method. The exact opposite is true if they're in parallel. If they're in parallel, you treat them like series resistors and you just add them up. Okay? Everybody clear on that? That may sound a little bit confusing. Now, the main project that you're going to do in the capacitor project is you're going to build a circuit with a diode or two. And what is that doing? Creating DC power, right? You're building another power supply. Then you're going to take a capacitor, and it's going to be connected some of the time to an ammeter through a resistor and another capacitor. And when you charge up the primary capacitor and connect it to the load and the other capacitor and the meter, you can see the current flow. And that's the main point. And if you've calculated the current flow time period, you've just calculated an RC time constant. And we're using a really big resistor and a really big capacitor, 1,000 microfarad capacitor. And the resistor is 1 meg ohm. How many is a meg? Kilo is 1,000. Mega is 1,000,000. So it's a 1,000,000 ohm resistor, right? So to create your 1,000,000 ohm resistor, if we don't have one available in the lab, you could take 10 of them in series that are 1,000 each. And how much would you have? That's only 10,000, so you'd have to have 100 of them in series? Wow. You sure about that? No, that'd only be 100,000. You need 1,000 of them. So building a series set of 1,000 ohm resistors to get a meg is not going to work out. You'd have to have 1,000 of them, because it's 1,000 thousand. That's what a million is, right? 1,000 thousands. Okay, that's an engineering notation thing where we need to know what that means. Now, if you have somewhere near a meg ohm and you have somewhere near 1,000 microfarad, you're going to have a good solid time that you can look at for a good solid, well, we won't talk about how long because that's what you're supposed to figure out in this project, right? So, do you have to have an exactly 1,000 microfarad capacitor? No. Do you have to have a meg ohm exactly resistor? No. Do you have to have something close? Yes. Now we have 1,000 ohm microfarad capacitors in the lab, so that's not a problem. I'm not sure we have meg ohm resistors, but if we had, say, a 500,000 and a 500,000, are there 500,000 ohm resistors in there? Probably. Or some combination of it. So you get close. Now what happens if you have too low resistance? The current's going to flow faster, right? And your time constant's going to be cut down. So more resistance, the more time, right? The longer it is, the easier it is to see, right? And you need to come close from your calculated time constant to your visually timed. We're going to literally time it with a stopwatch or your smartphone or something. and we're going to time it and see how close it is to your calculated time constant. Oop, almost yanked the computer off the desk. Okay, so there we have it. It's not a hard project. It's just slightly difficult to understand. All right? Everybody good with this? All right, so that's basically what you need to know to start this project, I hope.